Yeah, I'm going to discuss today some of my efforts using COMSOL modeling for optics processing and how that can support, high-power laser systems, aka the NIF. So I'm from Lawrence Livermore National Laboratory, and when most people think of LLNL, I'm imagining, especially in this audience, betting the first thing that comes to mind is NIF, National Ignition Facility. And I'm also betting most of you have heard about the shot that happened almost a year ago now of a yield of 1.3 megajoules, which was a 25-fold increase over the previous record from a few years prior, 2018. But I did want to take this opportunity to also highlight some of the other systems at the lab, right? It's not just the NIF. There are high-energy petawatt class lasers like ARC, as well as a high rep rate petawatt class laser, HAPLs. And so, the lab is really pushing the limits of attainable energetics across the whole spectrum. And so I brought a little bit of a dated video to kind of give an overview of the NIF, but I think it really goes into a lot of the details that I think people might appreciate in terms of the scale of the system and what goes into making NIF happen. So if you could go ahead and play that, I'd be ever so grateful.
The universe, for billions of years, has been lit by the fire of countless stars. In these stellar cauldrons, hydrogen nuclei are fused together to form helium nuclei, releasing energy that lights the heavens. Can we build the technology to harness this awesome energy on Earth? As we approach our planet, that is exactly what's happening today. Far beneath these clouds lies the National Ignition Facility, located at Lawrence Livermore National Laboratory in Livermore, California. This facility has been built to bring star power to Earth. It is the world's largest and highest energy laser system. Containing 192 laser beams, NIF will explore controlled nuclear fusion to ensure global security, enable sustainable clean energy, and advance our understanding of the universe. 85 feet tall, the laser and target area building is the size of 3 football fields. Inside are 2 parallel laser bays, each containing 96 beam lines. In this animation, which is millions of times slower than real time, we will follow the process for creating a miniature star in the target chamber by riding along with some of the laser beams. The process starts by first energizing the laser amplifiers in the 2 laser bays by dumping electrical energy stored in capacitors into flash lamps. They convert the energy to light that is absorbed by the laser glass in the amplifiers. Later, when the laser pulses pass through the glass, they will extract this energy, thereby increasing the laser beam energy. Our trip with the laser beams begins in the master oscillator room, where a very low-energy laser pulse is created. This pulse is only 20 billionths of a second long in duration, which is a beam of light about 20 feet long. It's amplified and then split into 48 laser pulses, which are carried over to the 2 laser bays using fiber optic cables. Here, the 48 pulses are amplified in a preamplifier by a factor of about 10 billion. Then they're split into 192 pulses and sent into the main laser system. As we track 8 of these beams through the facility, you can see the path of the beams highlighted in red. The first amplification occurs in the power amplifier. It has 5 glass slabs that were energized by the powerful flash lamps. Then they travel to the main laser cavity that directs the laser light back and forth 4 times through 11 sets of laser amplifier glass in the main amplifier system. This gives the laser beams another boost of energy. During this time, optical components ensure that the beams maintain their required pulse shape, quality, and spatial uniformity. On the final pass through the optical system, the laser light is allowed to exit and travel back through the beam lines and up to the power amplifier once more to pick up even more energy before heading down the long stretch to the switch yard. In total, the energy of the laser beams is increased a quadrillion times as they travel more than 1,500 meters from the master oscillator room to the target chamber. In the switch yard, the parallel bundles of beams are rearranged into a conical configuration. That's so they can be focused into the center of the target chamber and onto the target assembly. The assembly holds the spherical fuel pellet containing hydrogen. Here you see the 8 beams split into 2 groups of 4 beams each, one group traveling up and the other traveling down, heading for equidistant entry ports on the target chamber. Finally, the beams pass through the final optics assemblies, which convert the original infrared laser light to ultraviolet. The beams then converge on the 10mm target assembly called a holeron, generating a bath of X-rays. This causes the tiny target sphere to implode and ignite in a controlled, self-sustaining fusion reaction. The same process that powers the stars. This will be the start of a new journey that will bring not only discovery and innovation, but a lasting legacy to the future.
As we saw, it's a large system. 192 beams, and each one of those beams has some small optics and some large optics. In fact, it's the largest optical instrument in the world with 7,500 meter-size optics across all those beams and 26,000 smaller optics. And so there really is the question, how can 30,000 plus optics be maintained to achieve NIF's goals? So if we're talking about laser damage, then there's 2 concepts that we really need to talk about: laser damage initiations and laser damage growth. And so laser damage initiation, laser damage initiation is actually something that, over the last many decades, many careers have been spent working on laser damage initiation. So by minimizing scratches, doing some, chemical treatment of the scratches, and taking care of any sort of defects or, unwanted chemicals in the glass. Laser damage initiation, actually, if you can go back one click. So the red curve is the initiation density, or how many damage sites initiate per square centimeter at the fluence shown on the x-axis in 1997. And if we, move to more recent times in 2015, then we go to that purple curve, which is, shifts down and to the right. And that's really the space that we want to be in. But the stochastic nature of laser damage tells us that there will always be some laser damage initiation. So if we'll advance a slide, then that video that we were just watching is what happens if a small damaged site is exposed to subsequent laser irradiation, and you see that it quickly grows into something that is not so benign. And so if your optics on NIF have tens or hundreds of these, then you're going to be obscuring the throughput, which is not something that you want if you're trying to maximize, delivery to the target. So if we cannot avoid laser damage, and if replacing thousands of optics daily is just not economically feasible, then the question becomes, what can we do? And that brings me to the meat of my talk. And so laser processing can actually be used in both the initial fabrication and repair of large NIF optics. And so if we look at, not the wavelengths that NIF is utilizing, but if we look at mid or far infrared, out at those wavelengths, fused silica, which is the material I'm going to be focusing on today, absorbs light, and it gets hot. And those demonstrations on the bottom, there have been 3 demonstrations. So on the left figure, you see the left image of the left figure, a rough fused silica surface. But then, panel B is after, mid-IR illumination, so a 10x surface roughness reduction. And if we go to the middle figure, if you look at the top panel, it's not quite so clear to discern what we're looking at, but this is a cross-section of fused silica at an angled view. So if you see that white bar or my blue arrow, that designates the top of the optic, and traveling down along the z-axis, you're going into the optic. And so illumination with mid-IR laser is shown in panel D, basically anneals out the defect, or, you heal your fused silica. Or on the right-hand side, if you want to do a very thorough repair, if you take a CO2 laser and you raster scan it around a laser damaged site, you can basically utilize material removal to kind of micro machine or micro shape your fused silica, and in that image there, that image with the 1 micron 1 millimeter bar across, I just think that's a cool image. So that's showing your canonical pit after kind of this micro shaping. And so those are ways that laser processing can be used. But the question then is, what do we need to consider if we want to try to model this? And so we can break this laser material interaction into different regimes, basically governed by the temperature. So densification, or and from that fictive temperature, I'm going to go into more detail on the next slide. But that's something that we will need to include. Marangoni flow. So as your fused silica gets hot, the viscosity drops, at which point you might have surface tension driven flow, basically glass reflow. So that's a physics phenomenon that you might want to include in your model. Or if we take it to the other regime, high temperature ablation or evaporation is something else that you might want to include in a model to capture all of the physics. And so results that I'm going to be talking about today are this low temperature regime, and low is relative. This is still 1800 C or 2000 C, but this low temperature regime for smoothing or polishing. And the figure we see on the right-hand side is kind of like the gold standard for CO2 laser fused silica interaction. This is a figure I pulled from Ryan Vigne's paper from a decade ago. And so you can imagine there was a CO2 laser just parked on top of the fused silica. And what we're looking at are the surface profiles following irradiation. So you see different powers cause different levels of deformation in the fused silica surface. So if you can take advantage of that, then you can basically polish an optic with a laser. And so that's what I'm going to be discussing. And so to better understand that, there's a concept of fictive temperature that we really need to take a moment to explain, because that's going to come back up over and over again. And so the bottom left plot is the expansion of fused silica as a function of temperature. And fused silica is an interesting material. If I bring your attention to the curve with the blue dots, when you heat it up, initially it expands, as you would expect material to, but then there's an inflection point. And if you continue heating it, the fused silica kind of reorients itself into those rings, as you see there above the LDA, right there. And if you heat it up more, those start to kind of collapse on themselves. And that phenomenon is called densification. And so if you, right where that mouse is pointing, if you get there and then you cut off the heat source, there's going to be a competition between material relaxation, which would love to go back to that equilibrium state, and the viscosity, which is going to be increasing now that the heat source is off. And in fact, depending on how you terminate the heat source, that viscosity may be increasing very rapidly, which basically traps the fused silica structure in some orientation that's different from the initial equilibrium orientation. And the point where that structure gets trapped is kind of in what we call the fictive temperature. In other words, the fictive temperature is a metric to describe the state where the fused silica it got trapped. So the fictive temperature is not something where I can take a thermometer and measure it. Rather, it describes the state of the fused silica. But the fused silica is in this densification regime, which is governed by the fictive temperature. Then you can get from that the polishing depth. And if you have densification, then you might have some areas that are locally densified, and then some areas where there's no densification. So then it stands to reason that there's going to be residual stress. So there's a lot of things that come from being able to predict what the fictive temperature is going to look like. So thermoelastic and viscoelastic models were developed to simulate the CO2 interaction of glass. In the top left image is probably one of the more boring images on the screen. It's just a thermal profile with the stationary CO2 laser solving the heat equation. And on the right-hand side are fictive temperature outputs. So now fictive temperature, maybe you didn't catch it on the previous slide. I think I've got it on the next slide. It's governed by a diffie-Q. So adding a pair of ODE modules to the model, the fictive temperature is solved for. And what we see in the top panel there is the bird's eye view of a fusilica, where a Gaussian beam started on the left side and raster scanned across to the right side. And it's abruptly shot off on the right side where you see that red circle. And so it has a very different cool down there where the laser abruptly shuts off versus traveling on through. So we see that reflected in the fictive temperature. And in the bottom panel is just a cross section. So the model outputs are the fictive temperature that we see here, mass loss due to evaporation, which is included within laminar flow and a microfluidics module, and Marangoni flow, and densification. And I'll show you in a slide or two that densification is done post-processing, which really helps with the simulation time. So we have a model that can output the fictive temperature, great, but to inspire some confidence, we mapped it out and compared it against measured fictive temperature. So the right-hand side, the red curves are the model that's predicted, and the black curves are fictive temperature measured by Raman spectroscopy. And so those agree well. And there's those equations that I referred to on the prior slide for those of you that just like to get into the math a little bit. And so from the fictive temperature, I mentioned that we can get the polishing depth and residual stress. And so I'm not going to walk us through all of the math, but where you see the green arrow on the right-hand side of that equality, basically that's an expression that we can integrate. And so from the plot on the right side of the screen, it's the empirical relationship, how the density changes with the fictive temperature. So knowing that empirical relationship and the fictive temperature that the model outputs, we can predict what the polishing depth will be. So on the bottom row is the polishing depth. Basically, this is the surface deformation in the scanning direction, which is right below the fictive temperature plot. And on the right-hand side is the transverse scanning direction, or perpendicular to the scanning direction. And so this gives us our polishing depth. And now that we have this semi-analytic model to give the polishing depth, of course, we wanted to validate it, so we compared it against the Vignes paper that I alluded to earlier, which is kind of the gold standard. And so on the left-hand side, on the top row is the Vignes paper, right-hand side is the model, and those horizontal lines of different colors are just to guide the eye, and it agrees well. And in the bottom row is some of the measurements we did in-house. So black curves are white light interferometry, and red curves are the polishing depth predicted by the model. And so we used a different kind of fusilica. There's 3 different kinds of fusilica. So what we were using in-house was different from the Vignes paper. So we had to go through and get the fitting parameters for that. But it agrees well again. And I should throw out the disclaimer that for the semi-analytic model, there's the caveat that it needs to be done with the subablation regime. So this all comes from the change in volume. So if you're evaporating or ablating material, that will be problematic, and then we have to go to a different model that we have. But for the work that I'm showing here, we just wanted densification for the effect of polishing and smoothing. So we were subablation, so that's why this model holds. So these are a couple of optics that were polished in a lab setting just to demonstrate. And so the starting surface, I'll bring your attention to the ground surface, which is kind of the bigger image in the middle there. And then on the right-hand side, those are 3 optics with 3 different laser polishing recipes. So on the leftmost of that tiered stage of images is a coarse ground surface that was laser polished. And if you look right smack dab in the middle of those optics, you'll see a little circle, because this was all done with annular scanning. So that if you look in the middle, that is how the optic started pre-polishing. So we see with power 1, which is going to be, we'll just call that the low power, there was some polishing. But if we go towards the middle, which is a coarse grind fusilica, but a higher power, there was even more polishing. And now you can see some areas where there's optical transparency. And if we go to a fine grind initial surface with a low power, that optic actually was in typical optical specs. So that was pretty exciting, and we were able to take the results from the model and put it into practice. Where can we go with this model next? So we discussing densification, which is what's giving us our polishing depth. But you can imagine if there's densification, which will be dependent upon the fictive temperature, which will be a local effect, then there's going to be local densification. So there is definitely going to be some residual stress. And then the two plots on the left-hand side are from that Vignes paper, just to show the stress profiles. The top one is after laser exposure, like immediately after the laser was turned off, and then the bottom one is after the optic cooled back down to room temp. So we do see some residual stress. And for some applications, that could be advantageous. But for most applications, you're going to want to avoid that. And I should mention that in the earlier mitigation processes, I mentioned the micro-shaping of fused silica to basically remove damaged area. In the first generation processes, residual stress was not taken into account, and those optics actually failed. So it's very important. And from the fictive temperature, you can actually work your way back out and get the residual stress. So that is an area where, moving forward, COMSOL can further aid in narrowing down the parameter space. And on the video here, in the beginning of the video, you'll see the laser scan across the surface, and you'll see the residual fictive temperature. That's what's plotted, fictive temperature. And then a little bit later, there's a large beam laser that's annealing. If you're going to use a laser to polish your optics, you would probably rather use a laser to anneal your optics. It's simpler. You can use it in the same setup. It could be much, much faster, like hours, days faster. And so there's a lot of advantages for using an annealing laser. So what that simulation shows is at the end of it, what you would like is a uniform fictive temperature across the radius of the optic. And you see, it's a lot more uniform. And so COMSOL modeling can help narrow down that parameter space to even further optimize that. And so actually the next slide is my conclusions. So I think I am over.